Hello, welcome everyone. I am Marie with Karim Azoum from the French Competence Center. It's part of the EuroCC project. And with Pierre Aubert from the lab in Annecy. Together, we organize the Grey Scott Thursdays and the Grey Scott School. So welcome to this new session of the Grey Scott Thursdays. As always, those weekly webinars explore the key topics from the Grey Scott School program and progressively can prepare you for the summer school. And a quick update before we begin, the registrations for the Grey Scott School are open and there are still a few spots left in Annecy if you'd like to attend on-site in France. So be quick. If you're interested in hosting the school too at your institution, it's possible. It's very easy to set up. And we are organizing with Karim an information meeting on Wednesday, 15th of April this month to walk you through everything. I will share all the useful links in the chat. And of course, feel free to reach out if you have any questions. Those webinars and the school are free, open to everyone. So if you find them useful, please don't hesitate to spread the word. As usual, it really helps us.
Could a simple chemical reaction teach you how to unlock peak performance on today's supercomputers? Welcome to the Grey Scott School 2026, a free advanced summer school on high-performance computing, designed for professionals from industry, public sector organizations, and academia. From June 22nd to July 3rd, 2026, join us in Annecy, France at LAP, at one of our satellite sites across Europe, or online via live streaming. All courses are taught in English. You can pick the courses most relevant to you or dive into the full 2-week program. You'll learn the practical behavior of modern hardware and how to write performance-optimized portable code. Week 1 focuses on CPUs, Week 2 on GPUs, covering architecture, bottlenecks, parallelism, memory, and performance analysis. All learning is built around a single challenge, simulating the Grey Scott reaction. Simple to start, yet complex enough to stress compilers and expose performance limits. You'll explore modern tools, languages, and libraries such as C++ 17 and 20, CUDA, Fortran, Python, OpenMP, TBB, Kakos, PyTorch, and more. The school provides ready-to-use container environments for smooth hands-on sessions. Expert instructors from CNRS and CEA guide you with live Q&A and community support on Discord. Satellite sites let you learn together locally without traveling. Want to host one? It's easy with our turnkey setup, sharing the school with your colleagues and ecosystem. You'll leave not only with hands-on HPC skills, but also an official certificate of participation. And you know what? You can start early with 18 Grey Scott Thursdays webinars, weekly from January 29th to June 11th, introducing summer school concepts and new topics. Whether you're an industry professional, engineer, researcher, or student, if you have programming experience and want to push your skills further, this program is for you. Register now at cc-fr.eu and start learning today. Grey Scott School 2026, Europe's leading HPC summer school.
And today's session will be presented by Vincent Lafage, who will introduce Fortran on GPUs, a key topic for the performance and portability in HPC. So now I will give the floor, as usual, to Pierre Aubert, the creator of the school, who will present you, Vincent, and the subject of today.
Okay, thank you, Mary, for the nice introduction. So you already know Vincent for the previous presentation, but briefly to introduce Vincent. So Vincent is an engineer at GC Lab. He worked on many experiments, mainly on C++, on Fortran, on ADA also as well. You know, he liked very well the precision of the computing, and really, it's really important for him and for all of us normally, but it's most important for him also. And today is the next part of the Fortran computing. So we already had Fortran on CPU, and now it's time to work on Fortran on GPU, because you can do lots of magics with the Fortran on GPU now. And all the wizardry, the word detail will be presented by Vincent. So Vincent, it's up to you. And if you have some question, you can use the chat as always, and we will answer all the questions at the end of the session.
Thank you, Pierre. Thank you, Marie. So today we'll address the other side of the sky after the CPU, the GPU, and always under the sun of Fortran. So we'll see the various ways to use the GPU with the venerable language, OpenACC, OpenMP, native NV Fortran, and some dab at CUDA Fortran as well. So, as was explained by Pierre last time, and we will re-scan the details. To get the best of your GPU, you need threads, lots of threads. We already have seen in Fortran how to express large parallelism. Semantics of the language is rich indeed, is rich in way to express concurrent loop, to express array expression. GPU in Fortran allows for problems of riches. We have a lot of ways to address the GPU from Fortran. So to get a brief overview, we could use OpenCL in Fortran. You have on GitHub lots of projects in the way, in the style of Fortran CL. But even if the very good aspect is we can use it with other GPU than the NVIDIA's, it's very heavy. In Fortran, it will rely on a C binding. And in the same way, Vulkan looks from the Fortran side as OpenCL. You can use it everywhere, but it's very heavy and relies on a C binding. So we'll just take a quick look at this and go to the most ancient way to use efficiently the Fortran language with NVIDIA GPU, CUDA Fortran. The nice aspect of CUDA Fortran is its large set of libraries. The most obvious sites are cuBLAS for linear algebra, with a 3-level, a QFFT for Fourier transform, and QRandom to generate lots and lots of random number to feed your many GPU cores. Okay, so obviously the problem is it's only on NVIDIA as most of the following solution. So OpenACC on its side is in some sense a higher level language. It's a set of directives that allows you to focus on the high-level aspect of expressing the parallelism, telling the accelerator, ACC, what memory is and what loops should be distributed over the accelerator, aka the GPU. So as the ACC directive were built on the same semantic as OpenMP, but OpenMP was only addressing CPU issues at first. OpenMP finally decided to offer OMP directive for GPU, for so-called targets. We'll see a quick example of this later. So the offloading model is a bit different, but not much. And finally, we'll conclude with NV Fortran, the NVIDIA latest compiler. So as the name implies, it's only on NVIDIA, but it's the most transparent way to GPU-ify. In some sense, it's an auto GPUification. And in principle, you have nothing to do. So we'll discuss also what is the size of this nothing. But before addressing GPU for themselves, I will recall the scales of parallelism. So usually we all started with processes for a long time in well-separated environment. So we can have so-called embarrassingly parallel problems. I don't see in which way they are embarrassing. These are delightfully parallel problems. In particle physics, in particular, we have event-wise distributing processing on a grid. Each node would have a long time ago only one CPU and would deal with only one process. So processes were multiply independent in the sense that they were not on the same machine, so they would definitely not share the same memory. So for particle physics, embarrassingly parallel problem, it was okay, but when you had to share information between the node, it had to occur over the network and was very heavy. So Unix offers inter-process communication in various ways: pipe, shared memory, semaphore, and you can go to the network with the various distributed memory systems such as a parallel virtual machine from 89 and a message passing interface, which is definitely the heavyweight contender in the arena. So from this, Fortran introduced cohere Fortran. So we'll not discuss it today, but we'll see it during the school. Cohere Fortran is a high-level language on top of MPI, considered as some kind of assembly for message passing. So if you want to do cohere, included in Fortran since 2008, you definitely have to master in some level MPI. So what we have seen already last time was how to use threads. So lightweight processes compared to the previous processes. These lightweight processes have a common memory. So contrarily to message passing, you don't have to organize the transfer of data. It provides you with a reduced overhead compared to a process. It was built on a POSIX thread, C++ thread, but some languages such as Ada had a very higher level representation with tasks in Ada 83 and protected object in Ada 85. The key point of thread is they have shared memory on SMP. So you can tell your compiler that this variable has to be shared, or this variable has to be copied. If you want to write in some shared memories, you will have race conditions, so you have to be very careful. OpenMP built on this system object to offer open multiprocessing in 97. And the two first languages to benefit of this OpenMP were C and Fortran. So another aspect that we'll go into more detail before entering the GPU proper is vectorization, because even threads have too much overhead when concurrent tasks are really elementary. We can use no CPU thread for individual sum or product of many data. So for vectorization, the level is instruction level parallelism. You had either a vector processor à la craie, introduce the single instruction multiple data approach, or for the case that concerns us, modern processor with fixed length SIMD. In the Intel world, it's MMX, SSC, AVX, and AVX 512. So what is instruction level parallelism? We all know from day one bit level parallelism. When we practice with binary mask, we can end on OR 8, 16, 32, or 64 bits in one instruction. Not logical, but bit field AND and OR are the bread and butter of any developer. In the same way, for vector instruction to perform fluently, as for bit level, the bits are aligned on memory boundaries, we need for our vector instruction, for instruction level parallelism to perform fluently, to align our vector of data on memory boundary. So we have better order data of the same nature as an aligned and contiguous array, which we have already discussed in these webinars. For data contiguity, we prefer a structure of array to the classical object-oriented collection of objects or array of structure. So contiguous rely on us, the developer, but alignment needs to have some pact with the system. We need to discuss these dirty aspects of alignment, which is a very low-level consideration and goes in the way of high-level language. So, how to vectorize? I would present vectorization as an industrialization process. You see here the main character being working on two nodes at the time. So it's a single instruction, single operation, double data. So you have to consider your computation as a production line to be in the mood for vectorization. You can also see it in a military way with a pincer movement around performance. Of course, you want to be parallelizing from the top, but you want to be vectorizing from the bottom, from the elementary aspect. And on top of this, you want to keep the cache hot. So this is the level of strategy you want for optimizing your performance. Okay, so practically, after this high-level consideration, how to vectorize, the first solution is to uncraft vector codes with dedicated low-level instructions, intrinsics. It's efficient, but very costly. It doesn't port well. The second way is to use vector libraries. It's definitely the easiest way. You transfer the problem to the library. And it should be easier to let the compiler do it, provided we can do two things. First, we have to express the data parallelism. So this is a high-level aspect. As we have seen in harnessing the powers of array, inspired from MATLAB and definitely in Fortran since Fortran IT. But we need this other low-level aspect. We need to provide to the compiler hints about the data contiguity and alignment. On this low-level aspect, we can do it relatively easily in C, but in Fortran, it will depend on compiler pragma, and GNU Fortran is not equipped with these. So once you have done all the things that in principle will lead to vectorization, you want to check. Programming is an experimental science. So how to check that our code, our compiled code, has been properly vectorized? So we have multiple ways as well. We need to use flags, compilers flags to report vectorization. We can check the resulting assembly, which is not funny. We will see also how to use Macao and indirectly perf. What is more, as I've maybe quickly said in my precision video, sometimes your computation relies on some kind of symbolic vectorization. The easiest aspect are complex numbers, but of course, quaternions are even more significantly impacted. So it's a symbolic vectorization because your complex computation process two inputs, real and imaginary, at a time for each of your symbolic computation. The big problem is that this symbolic vectorization gets in the way of practical vectorization. Because to implement classical complex multiplication formula that you see here developed, we need the complex of vector rather than a vector of complex, as we have said. So you want to have A1, A2, A3, A4 contiguous and not A1, B1, A2, B2, A3, B3, A4, B4. Okay. So, which means that your vector complex library will be a full rewrite if you don't benefit from such marvel such as Eve library. Okay, so in Fortran, what does a vectorizable code look like? So sorry for the very small characters, but you see function loop cube root. It will compute the cube root of an array, tab arrays, which is provided with generic dimension, and it will take an array tab A and return a tab arrays, two contiguous arrays. So inside we have elementary scalar variables, we have integer variables, scalar variables, and we have some parameter provided directly with their FP32 binary representation translated from hexa to real 32. This transfer, this real parameter constructor, array constructor, is in fact a kind of cast. Okay, and then we have a loop, and we take the element of the array and have a lot of operation. Okay, some of them are floating point, some of them are integer operations, and in the continuation of this code, the follow-up is some Horner scheme computation for the first approximation of the cube root, which is later refined with a 2LA iteration, providing cubic convergence. If you have so many correct digits in the first iteration, you have 3 times as many correct digits in the next iteration. So Alley iteration is very powerful. It's costly, but as you can see, there will be a division. This is the big part of the cost. So we transfer back the byte representation to real floating point format, and we fill the result. So nowhere have I written anything about, you see, special instruction for vectorization. I only told the compiler that I swear the data are contiguous. Okay, so is there just to compile? Yes, but not quite the magical operation. We have a lot of flags to activate. Of course, they depend on the compiler. Here are two examples on how it can be executed. Did it work? We can disassemble the binary and check for the proper routine that we want. The name is mangled because this function loop CBRT is part of CBRT module, so hence the peculiar name. But the good news is you see that of course, the instructions start with V, but they have a PS packed on the, so they are not single scalar vector, which are not vectors. So here we see that we could use ZMM registers. It means that we are using AVX 512, best of the best. Okay, so we won. Okay, we want to forget all hope entering the hell of vectorization, and the best way to mutilate this hope is to use Macao. It's a performance analysis and optimization framework operating at binary level with a focus on core performance. It mixes both dynamics and static analysis based on its ability to reconstruct high-level structure such as function and loop from a binary. What does it look like? So we ask Macao to do some code quality analysis on the same function loop. So you see the name mangling that is, I consider, not easy to guess. So you need to practice obj dump and all the things that you want to look at the inside of your binary. You provide Macao with a request for hints and expert advice on to follow calls, and in the end, the executable. And among the message, you find this. The good news is here in vectorization, your loop is vectorized, but using 98% register length, which is an average across all ACC AVX instructions. By fully vectorizing your loop, you can lower the cost of an iteration from 37 to 30 cycles, so it would be a 3% speed up. Maybe we are satisfied with this level of speed up. We can do no more. So the 98% is the good news. The less good news written over is that the main loop, which is unrolled by 16, so we address the cube root of 16 single precision floating point number in one go. This is enormous, but given that we have a division in the process on other instructions that don't mix well, we can only output less 1 out of 5 out of the max floating point operation per cycle. Okay. Then Macao is very good at advising. He provides us with workarounds and tells us that use vector line instruction. And as I have said, we can deal with contiguity in modern Fortran, but we don't have a standard for addressing memory alignment. In particular, the GNU Fortran compiler does not support allocation alignment and does not feature directives to benefit from all of this. So this is what we feared from the start. Macao is not worried by this. It tells us, oh, use another compiler or locally use C code, for instance, via library. So maybe this would be in some more extreme case a good thing. But okay, we still got 98% of vectorization. That's good. Okay, so the Macao also addresses the execution unit bottleneck and tells us to reduce the number of FP multiply and FMA instructions, but okay, the computation we want to do requires them. So what is more? We get from Macao in expert mode the same disassembly. So the address that we had 13B8 that we had guessed from the surrounding is indeed the good one. And as you see here, most of the instructions are 100% vectorized, except those two of VP mule DQ and VP mule DQ. Okay, so that's it. We know where is the culprit. Okay, so when you ask also for more details, Macao tells us that he detected complex instruction trees that generate more than one micro operation, and only one of them can be decoded during a cycle. So yes, I don't think that for two occurrences of this complex instruction, I will have high-level control over the use of such. In the same way, tells us that he detected two unaligned load and store instructions. But once more, this is the same workaround. We have a problem of high-level language not mastering the low-level aspect. Okay, so a lot of reports on the arithmetic intensity, 2.67 operation per loaded or stored byte. We are far from 80, but better than 1. So why did I spend all this time on a GPU talk addressing vectorization? Because as Pierre nicely introduced in his slide about GPU architecture, we have a very large vector unit when we think about a GPU. So the GPU has its memory and the streaming multiprocessor. On each of these streaming multiprocessor has a set of cores with execution context and shared memory. And this core operates as one vectorized core in some respect. As Pierre nicely described, in modern GPU, you have even higher level organization of the streaming multiprocessor. So Adrien pointed out this translation matrix between CPU, NVIDIA GPUs on more general point of view on GPUs, Chronos, OpenCL, SQL, Vulkan. So use this as a Rosetta Stone of the vocabulary that is very vivid and very poetic in some sense. And we go from the poesy to the dirty aspect. I will not enter today in all the detail of GPU setup. When developers get their hands dirty, you can ask when things have finally been properly installed, what is the NVIDIA SMI status of your machine. You will get the number of the driver, 560 and something, the CUDA version, at the time it was 12.6. In order to see all these reports, you need the good kernel module, so you can get info with user has been modinfo NVIDIA current. But your good kernel module has to be compiled with the right kernel that have some window of compatibility between them. It has to be installed with the right CUDA version. It has to also have the right CUDA compute capability that is not apparent from here. You go to the provider NVIDIA list to see that your RTX A4000 has this or that compute capability. And you also need the right NV Fortran version because more modern NV Fortran renders obsolete old GPU. So if you have an old machine with a working setup, don't hurry up upgrading your NVIDIA HPC SDK. It could render your GPU useless. So all those aspects are really tedious and needs strong and close cooperation with our colleague from network and system operations. So when you have a Fortran program, so we have seen that it's not always obvious to vectorize it, but if you want to GPU-ize it, in particular when your GPU would not be NVIDIA, you have a lot of smaller GPUs in many aspects, how to proceed. So popular version in C are OpenCL and Vulkan, the modern aspect. And we can decide to go on the modern Fortran way using ISO C binding and translating one after the other each Vulkan constant, so some simplified example here. We can also simulate Vulkan types using only necessary fields. So 2 examples are given here. And with this translation module, this thin binding module of Vulkan, you can write a program to display image on, you will start declaring interface for the legion of Vulkan functions. So here is only a small example on, okay, you see this program start with, in fact, pages of interface redefinition before programming anything useful. It's very heavy, it's very administrative. If you need it, go for it, but it's painful. Okay, so now let us try to have something more usable. Let's get satisfied with the fact that, okay, most of things will operate on NVIDIA GPU. So you can use, in the same way there is CUDA for C, kind of extension of C language that allows you to see what, how to transfer data from the GPU from the CPU to the GPU and back, how to program something on the GPU. So very early, CUDA Fortran appeared, which is the same as CUDA is for C, but for Fortran. So here we'll define, so sorry for the standard theme of this school with Adamar product. I will here show only SAXP usage, which is not far from Adamar product. So you provide 2 vectors, one of which will be modified, y, and some constant, a, and you define here some pure subroutine which has the attributes global. So this is not standard Fortran, this is CUDA Fortran. So that's why you need the NV Fortran compiler. What we see is that we'll be looping on all the elements of the in vector. We expect that the in-out vector has the same size. And as long as we don't exceed the size of the input vector, we compute the index from the block index and the thread index. So as we have seen, the streaming multiprocessor is the physical unit, and the corresponding logical unit is a block. All your warps that will be all your threads that will be executed on cores are united in the same block. So here we don't show any loop, but basically we are looping on I, this index, and the CUDA Fortran compiler distribute the computation. You have not expressed any loop explicitly, but CUDA Fortran translate your kernel, attribute global is for kernel. Donc CUDA Fortran attributes this to enough blocks and enough threads. So this is not only a change in the syntax of Fortran with this attribute and some other aspects that we'll see, but this is also a change in the way Fortran expresses the usual concurrency. So the previous module, in which we will use only the SAXP function, can be used in this example test SAXP when you define 2 arrays of real single precision with fixed size and some value, and then you define on the device, which is on the GPU, 2 other arrays, 2 corresponding array. So you see this extra attribute introduced by CUDA Fortran, which is device. And you also use the CUDA function dim3 that you will use to pass to the system the size of your blocks. And you compute the grid of blocks in this way. Your 40,000 elements will be distributed in blocks, and in turn, these blocks will be distributed over threads. So besides some peculiar aspect, you transfer the data with X on the device is X on the CPU, and this is translated to some data transfer from the CPU to the GPU. You initialize your array on constant first, and then you pass it to the GPU. You call the SAXP with this peculiar language, lesser for the kernel, that requires not only the data, the standard argument of a function, but also the way that the GPU should split this computation. And in the end, the data you recover on the device with YD is transferred back to the CPU on Y. And you can check the max value error is 0. Okay, so this is a elementary CUDA-Fortran program. I like this example because it shows you that if you want to use CUDA-Fortran that has an excellent performance, you have to change your way of thinking your computation. This is a kind of major rewrite of your function. Okay, so as we discussed last time, I wanted to operate on some large theoretical computation. I first tried to multi-thread it with OpenMP. A lot of questions occurred, and in the end, I turned, in fact, to rewriting the whole code in more vector-friendly way. On top of this vectorization that provided me a factor 2 speed up, which is nice. So I went from a 52 speed up to a 100 speed up before using the GPU. And then I wanted to GPU-ify my vectorized code, and we can do it with ACC directive. So the first one we will look at is this one here with the parallel loops. The first syntax telling the compiler we will collapse the 3 following loops, okay? And then inside we will collapse independently the 2 following loop as an independent vector, and we express this computation. So a sum of products of things which are looped over with 2 loop nests, you should tell me, okay, why didn't you use matrix multiplication? So at the time, the compute capability of my GPUs did not allow me to have matmul understood for GPUification. So this will be a recurring theme when you want to GPUify Fortran. In fact, it's you are living in some work in progress. It is a work in progress for the 15 last years almost. We benefit each year of major progress, and we have to get satisfied with this, but it's not quite easy. So before addressing the concurrency of the loop, so you see we have standard Fortran 77 loops, at least. Let's say Fortran 90, as we use no number. It's not Fortran 66, and as we use this label to get the code clearer, this label makes it Fortran 90. But okay, this is no do concurrent in this. And in fact, ACC directive are incompatible with do concurrent, which is surprising. So we'll have to address this. Okay, smaller snippet of code that the people following the school will understand this summer. You see, we specify which data are on the CPU and which are created directly on the GPU. So the copy will copy the U0 from the host to the device, and the create will create it directly in the GPU memory, avoiding one transfer, which is nice. Okay, in this evolve library, your accelerator region is here. We call compute. So when we execute compute, we are in some concurrent region, and we have the same parallel loop collapse of these two. And in the same way, ACC does not allow for do concurrent. And we have a stencil kernel for Laplacian computation, which is small, nice, elegant. You can use it easily and express it with minimum effort of 3 ACC directives. Okay, 2. Of course, as ACC got inspiration from OpenMP, and OpenMP didn't want to miss the train and wanted to provide also computer accelerator offloading, which is GPU offloading. You have a slightly different syntax with OpenMP. You have OpenMP target data on map to instead of copy, on map from instead of create. The same end of the parallel region for the data, and the compute that is called in it will have a OMP target, teams, loop, collapse, bind teams. So the vocabulary is peculiar, but the syntax is correct. So it's a bit different, but not much. And we finally take a look at the easiest way to go. No directive, no ACC, no OpenMP. We replace our old nest of 2 do loops with 1 do concurrent nested loops. We have still the same expression. So in commentary, you can see the old way to compute lap view, but okay, be modern, use sum. Instead of 1, 2, 3, 4, 5, 6, instead of 6 lines, you get it expressed in 1. So be modern, use array expression. It's a must. And in 4 lines, you have expressed your kernel. You have not discussed the transfer of data, anything. NV Fortran, with the proper option, which is some know-how in itself, will automatically translate this to the GPU. So for a minimal cost, NV Fortran allows you to really benefit from a GPU acceleration, get your code clear, not really portable because it's only for NVIDIA GPU, but okay. This stays at a level of clarity and understanding that we can manage. And I will conclude briefly for once about a general statement for using GPU in Fortran. So we didn't hide. There are practical problems. So NV Fortran is a very surprising compiler. It is aggressively optimizing things. So I didn't enter in the details of NV Fortran for vectorization, but it was surprisingly good. It has a lot of optimization, and it is the only one to master this kind of auto GPUification that are marvel. But the most recent aspect of Fortran may not be implemented. You see, after 70 years, Fortran has lots and lots of libraries. So I hope that someday I will have time to discuss the implication of the recent upgrade of mathematical library as far as correct rounding is concerned. But we can look at the detail and see that each Fortran compiler gets its own implementation of the mathematical function. So 2 Fortran compiler may not provide you a bit-for-bit equivalent value. Only a very limited number of the compiler capitalizes on the C library, but after all, why not? Fortran is not C. Maybe Fortran has higher standards for accuracy. Well, in fact, nowadays, some liaison should occur on, let's say, not only this aspect of precision are important, but we also have issues with which functions are usable in parameter definition. For C++ people, it be which Fortran functions are const-expert by the compiler, and not all of the standard library is const-expert in this respect, which is a pity. But also, NV Fortran is, as far as I know, not yet implementing co-arrays. So this can be a problem. You can always do MPI in the old way, but at some point we'll have to use multiple GPU on the same node, and for this we will need different processes dealing with different GPU. So we'll stay with MPI for NV Fortran for some time. And even when you manage to have the right amount of parallelism expression, when you have billions of loops to distribute, then you have to do some tedious work so as to not overflow your GPU memory that is limited, and now not only limited but expensive as well. And all this aspect goes against Fortran's purpose. So Fortran purpose is to be a high-level language to express things almost at the mathematical level of the formula, and we would like that the compiler deals with all these tiny details. This is not yet the case, and this is something that is true for most GPU application, whatever the language. You have to get your hand dirty, not only for installation, not only for distribution, but for the maintenance of a system, for the evolution of a system, and for the expression of your computation. You have to go into the detail. Does it mean that we need prepilers or domain-specific languages to help? This would also go in some respect against Fortran purposes, because in this case, the DSL has the semantics and the Fortran is only some intermediary step, which is not the goal of a high-level language. It can be a solution to address your problem with a DSL and get one part of your Fortran code being automatic Fortran written for this respect. So as a conclusion, I would say that use GPU in Fortran, prepare some gallons of blood, sweat, and tears, but we have seen that it is very nice. It provides easy access to performance. It provides expressing a clarity of intent, but there are tedious issues. Thank you.
Thank you, Vincent, for the nice presentation. Oh, we already have a question from Leonidas. Thank you, Vincent, for another great presentation. Early in the presentation, you mentioned Vulkan as a possibility, but you didn't recommend it. Despite that, is Vulkan available in supercomputer with GPUs?
Okay, so I will confess that I'm not expert on this. I will have to try to build up a Vulkan image. So my initial intent with Vulkan was I was working on some experiment that had to be on board Odroid N1 Plus, and so with the collaboration of Pierre, we vectorized the C version of the computation. So it was certainly more direct to do it in C for multiple reasons, some technical, some political. The physicists would have frowned upon the use of Fortran in online computing, but so we had already the required speed up with this using only one of the 6 core of the ARM A73 or 52, but the Mali G2 GPU that was on this card, so it's obviously not NVIDIA GPU, was sitting idle on. Definitely, if I had time, I would, if I had to practice with Vulkan, I would proceed this way. So, as I said, and I try to summarize it again, I would use Vulkan at my level, which is not expert of Vulkan or OpenCL or even more OpenGL. I would use it if the easier form that I have described here are not accessible. Okay.
Okay, maybe it was more a question for Adrien.
Yes, certainly.
But the short answer is normally GPU people are forced to follow the standards of Vulkan, but sometimes it's not as fast as the proprietary backend. So, but normally you have a nice portability with Vulkan. So you have to check. Question from Philippe. Thank you for your presentation. What is your recommendation to get portable code on different GPU vendors, NVIDIA, AMD, Intel? For example, OpenACC support will disappear on AMD GPUs with the end of the Cray compiler for end at 2026.
So
you still have
here I'm sorry because yes, as this talk exemplifies neatly, we are really in the end of compiler manufacturer. So some things I have not tried yet is using the OpenMP directives, target directives from G-Fortran, for instance. In this respect, maybe it works. But you see, the setup is so heavy that compiler writer try to pave the way for you so that you only have to roll your computation. So for what I have seen, all the GPU computation in Fortran that I have seen have been built from scratch. And so I have not yet tried any realistic paradigm shift, moving from NVIDIA to AMD. So the CNRS Fortran team recently, last week, I bet provided the list of compiler. So I was using the AMD AOCC, AMD optimizing compiler collection, which is kind of long. So I'm always cautious because F-long describe different compiler in themselves, but I didn't know about the HipFort compiler. So the Cray compiler that you describe, I've not had the privilege of using it, so sorry, not better. So for OpenACC, what I did in 2018, I was compiling it with two compilers. I was compiling for NVIDIA, okay, but I was compiling it with PG Fortran, which was the ancestor of NV Fortran, and I was also compiling it with G Fortran. The result was not, certainly for a lot of setup reasons, not executable, but G Fortran would stick much more to the letter of the norm, OpenACC norm, and providing me hints that NV Fortran did not provide me. But of course, it's very disappointing to use a compiler only to know what the other has not told you, and that the result is not working.
Okay, maybe there's no more question yet, but I'm pretty sure there will be at some point. So maybe I can put in the chat the command if you want to get the compute capabilities from your GPU directly with NVIDIA SMI. So it's not by default, unfortunately, but if you ask it gently, normally you should get it. So the --query -GPU equal names and compute caps, and then you can get directly the compute capabilities without writing a discovery program to see the compute capabilities.
When you execute this NVIDIA SMI, it tells you that format equals switch is missing.
I just check it on mine. I have NVIDIA SMI. I don't know which version, of course, because
yes, that may be an issue.
Maybe I have. Could have 13. Maybe with the previous one, it's not possible. Yeah, I have the last one. Not exactly the last one, but I'm working on it to play with the really latest news. CUDA 13.3, I have CUDA 13.0, but yeah, maybe it's really recent. Maybe.
That must be the issue because I'm stuck with CUDA 12.6.
Okay. So maybe CUDA 13, you have good news at some point. Okay, question from Julien. Thanks for the nice talk. I am not very familiar with Fortran at all. A beginner question, what are the advantages next to C parallel possibilities?
Okay, so you can have OpenACC, OpenMP in C. You need what Pierre described last time for C++, if you want the equivalent of STD parallel, standard parallelism that you have in Fortran. So yes, my answer will be as usual. You benefit from a higher level point of view. So it's not a moral judgment of level. It's a level compared to the memory model. Fortran is farther than C from the memory. It tries to hide the detail. It was designed for mathematicians, physicists, engineers, rather than a computer developer, information technology engineer that appeared later. So it has good aspects in the fact that you don't need to bother with pointers most of the time when they are not needed, contrary to C. For a long time, you could do a lot without memory allocation. And we have seen last time that modern Fortran memory allocation separates two kinds of things. The memory that you will explicitly deal with, for instance, if you allocate a Fortran pointer, but if you allocate a Fortran allocatable, it can be auto-allocated on the spur of the moment when the execution knows the size of the right-hand side. It will translate to the side of the left-hand side automatically. And this allocatable function have a limited scope, so you don't have to manage the freeing of the memory. So these high-level aspects are more modern and easier for beginner. So in C, you have close control over what is appearing. In Fortran, you let the compiler work for you.
And also you have a lot of already optimized kernel for GPU, so the matmut, the transfer, the dot product, the reshape, everything. You have tens and tens of kernel, so you can already use. So you don't have to change your code. You use this kernel and then you change the compiler and it does the magic for you.
It would be telling, but as Pierre mentioned last time, on the first year we managed to get NV Fortran in the Grayscott school. We already had very good performances. That
you get the best performances of the school at once. Even if we struggle for weeks together to make sure that we understand what's going on. But yeah, it was it was really powerful. Okay, question from Michel. Using high-level libraries like Magma helps to run on AMD GPU, but then the burden is on installing that library. Okay.
I can understand this. So when we operate such computing accelerator, we rely on very specialized hardware. We need the help and understanding of our colleagues from administering system on the network.
Okay, question from Frederick. To port a legacy Fortran code on GPU using OpenACC, should we concentrate the parallel loops on the loops at the deepest level of the code, or can we use the feature for the directive language which allow calling routines in parallel sections? Maybe a graph, a CUDA graph in Fortran, is it possible? Or streams in Fortran, CUDA Fortran?
Oh, okay. So up to now, I have provided you with elementary roadmap that you see on the CPU side. I speak of a pincer movement between high-level thread parallelization and low-level vectorization, and more or less GPU addresses data parallelism, so low-level parallelism from the bottom. So in order to build some experience, you may want to start from the deepest level of code. But yes, okay, a nice research project.
Okay, so Julien is happy. We have François in the chat. François, NVIDIA engineer, if you don't know him.
Okay.
Yeah.
Good
He
news.
actually, yeah, help us a few times for compiling, for kernel stuff, once you want to profile stuff like this. So nice to see you here, François. So if you want to read, it's an article about Korai, but we will see that in the school a bit later, not in this webinar because we don't have time. But if you are curious, you can have a look.
Sorry, François, if I didn't honor the value of the most recent development on Core Fortran and NVIDIA GPU. I did not go forward very far this year about this.
Oh yeah, so yeah, a point about NV Fortran that we discover is if you have the habit to use tables in Fortran, which is, I think it's quite natural for Fortran programmer to use tables and table expression. You still have to, as you mentioned, explicit the do concurrent to be sure that everything will work. Otherwise, the GPU, the compiler does not care about the GPU. I say, okay, it's a table expression. I don't want to GPUify it. So yeah, it's you have to break a bit your table expression to be sure that the compiler will understand that. Okay, let's do things. In fact, yeah, you mentioned in the CUDA Fortran, once you can at once do a transfer just with equal or stuff like this. It's in fact it's quite similar to thrust in C++, much higher level than CUDA C++. In fact, so yeah, it's quite nice. But I have a question, a wizardry question about that. Can you directly with the Fortran syntax say, okay, I have my XD, for example, can I put a value in it, a constant value in it, rather than to put it on the CPU first and then you do the transfer? Can you say, okay, XD equals 1, for example, and directly on the GPU and everything is okay? Is it possible?
I would say most likely, yes.
Yeah, because it's Fortran, so normally the magic appear and
it would be translated with the equivalent of OpenMP create, OpenACC data create directly on the accelerator.
Yeah, you should be able to do some
magic. I will
yeah.
try it with this snippet of code. You see, 2 screens only. It only takes 1 hour to reboot your computer because the GPU is...
because you crashed your GPU. It happened sometimes when you try some stuff.
Okay. Beside this, it's at the tip of your hand to address, as any language, you have to proceed at first with snippets and build your knowledge of this new system.
Yeah, and here, as I will show also next week, we have to deal with the size of the grid and the block to be sure that everything is nice, and you have to compute it with the triple chevron call. You have to compute yourself the grid and block size. But okay, that's life. You have to deal with that. Oh yeah, I had a question. About Macau, of course. So you have to get the mangled version of your function. But normally, once you use Macao with C++, everything is mangled, but you just have to pass the function. Is it because there is a module that you need to do that?
I guess. So I did not push very far to decode this. So what I did was first using this, you always see the shared screen. I started with objdump disassembling everything first, and then I looked at my look CBRT, and then I found it mangled. So maybe there are tricks.
Yeah, you don't need to do it for C++. So normally for Fortran, maybe it's not mangled the same way, and
Yes.
Macao handle only the mangling of C++, but we have to check.
We have to check, but I would say if we try to summarize this experience of computing with vectorization or with GPU, so you have to do the back and forth between high level aspect, between precision aspect, between performance aspect, and low level aspect of the binary code. So it really is taxing.
And François, tell us also if you do the XD equal 1, it's okay. It's working normally.
Good news.
So it's possible. You don't have to allocate on the CPU and then do the transfer. You can allocate directly on the GPU and fill the values on the GPU. It's really, really powerful. And you have another CUDA Fortran article also from François in the chat if you want to have a look. Hopefully there is not too much spoil for the school here. In fact, you spoiled a bit the cubic root, the seminar of the cubic root you will make for the school, but just a glimpse, so it's okay. I'm practically done with my question, but maybe your last one. Once you are talking about auto GPUification and auto vectorization, of course we have to use tables. For me, it's quite natural to use tables in Fortran, but is it really natural for a programmer? Or once you want to port all codes in Fortran, do we have to struggle with that? Or is it quite common, in fact, even in the past, to use a table, and then if you want to vectorize, it's not that big of a deal?
Sorry, you mean table of parameters? You mean
a table of primitive type?
You mean array of
array of primitive types?
Oh yes.
It's
Array.
Quite common.
Array is the way. Fortran does not have collection for bad and good reasons. The bad reason is we still have to wait the implementation of Fortran 2028 that will provide multiple aspects on generics. We'll have generics in the Germano-Japanese way, and we will have generics in the American way. So we'll have generics as template modules, and we'll have generics as template function. It's very promising. We are waiting for it. And when you have this kind of parametric polymorphism, then you can have vector graphs, lists, hash map set in Fortran. Okay, that's not the point here. So the bad reason is we have very limited generic style in Fortran for now. The good reason is that it's very efficient to have array. They are contiguous in memory most of the time, even if modern Fortran allows you to have a kind of stride in this memory and cherry pick data at a regular interval. It's powerful, it's contiguous, it has solved a multidimensional array problem that C++ is not yet getting solved 70 years ago. So long life Fortran? Yes. So yes, primitive type array is really the way to think in Fortran.
Yeah, so normally, even if your code are really old, you use a bit of vectorization, GPUification, and normally that's it.
That's it.
A small do concurrence, small OpenACC, OpenMP, and normally everything should be okay. Okay. Or maybe a question from François is in the chat. Is it possible to do some some CUDA graph in Fortran? Yeah, because I did partially a small lecture last year for CUDA graph in C++.
Mm-hmm.
But
okay.
I don't know if it's possible in Fortran. It should be.
I have to recheck your lecture to
In
see.
fact, yeah, you have several ways to do CUDA graph.
Mm-hmm.
To express the graph, and of course you have the hard way and the nicer way, but you have to deal with the streams and stuff like this. But yeah, maybe we have to check, because if you start several kernels and the kernels do not fill the full GPU, maybe, as Stephen explained at the GCC also 2 weeks ago, it's a parallel by opportunity. So maybe there is a way to. Oh yeah, maybe related to that. Once you allocate on the GPU, can you pin the memory on the CPU as well? You know the CUDA malloc host, so you pin the memory, and then when you do the transfer, you can do the transfer at the same time, and you do the computing. And if you don't pin and you watch with Insight, you are sorry, because nothing is running as expected. So is it possible to pin also memory, or maybe since it's a trust-like API, it's done for you? Maybe we have to check with Insight.
Yes. A lot of minimal working example needs to be sacrificed on the altar.
Yeah. I think I passed through all my questions, so yes. So maybe if you have a last question in the chat, or maybe we can be happy to finish on time. Oh, François, answer to the question. So CUDA graph in Fortran. We have CUDA graph in Fortran.
Excellent.
Breaking news. Okay, so if you want to do some CUDA graph, some wizardry with CUDA graph, you can. So you have a lot of work for the school.
Definitely.
Okay, thank you, François. Okay, so maybe we'll stop here. We are practically on time. So thanks everyone for being here today, for attending this webinar. Thank you, Vincent, again for the nice presentation. Thank you, Mary, for the organization and for all the communication for the school and for the registration. So don't forget to register if you want to follow the school. And if you want to attend the school in Annecy, hurry up, because there is practically no place left. So think about that. And so next week we will do some wizardry in C++. So standard C++, C++17, ST transform, stuff like this. Also CUDA. I think maybe I will present a bit CUDA graph also, because it's funny and it will gain some time also for the school. So I will do the presentation next week. So a bit low level and high level as today, in fact, to have some part, maybe also some profiling to give you some hint. And of course you can profile everything you want, but we'll do some profiling, as Vincent mentioned a bit of Macau also. I will not have to do that next week, but I will do, I think, some insight, so you will have all the information. So how to profile to get a nice and to interpret also the timeline that Insight will give you. And that being said, I think it's okay. So thank you everyone for attending the webinar today, and see you next week for some wizardry in C++, CUDA, and Thrust, and NVC++, C++17 stdpar wizardry. Bye.
Bye.